So, would you like to introduce yourself first?
Yes. So I'm Francesco Fournier-Facio. I am a researcher in group theory, which is the subject related to this specific problem that OpenAI has solved. And I work at the University of Cambridge. I've been a postdoc there for 3 years, and I'm moving to Heriot-Watt in Edinburgh in October to start a professorship.
Oh, nice.
Um,
Congratulations.
Thank you. And this is a problem that I've been very interested in for many years, and I have been a bit in the middle of this in the sense that like I'm one of the people that saw one of the preliminary versions, and I know well the works that are being used here, and I take some issues with the way that that this has been presented, and especially the attribution. I think that
Uh-huh.
the main message that I want to get across is that it's very intellectually dishonest in the OpenAI announcement to say they say that this problem has seen no advancement in the past 10 years, and I think that
Okay.
is very dishonest because the proof relies crucially on advancements that happened in the past 10 years.
Are those advancements, are those recent results
Yeah, from
cited?
like I think the most they are cited. Yes, they are cited
Yeah.
in the paper, but in the official announcement it says that there has been no progress in the past 10 years. Um, and I think that this is most people will not look at the paper.
Right.
Most people will just read the announcement, and so I think it's important that people are aware of this. That this is like it's building on work that the math community has done for many years. And I think it would not have been possible without this work. So, and
Okay.
this is not work by myself; it's work by other people that I think should be getting a lot more credit from the get-go, and not just once you get to read the paper in detail. Yeah.
Yeah. Absolutely.
Okay, yeah. So this is a result of a group theory. So let me just really start from the basics. What group theory is? So formally, this is the definition of a group. It's a set with a binary operation that has certain natural properties. So it should be, it's a binary operation in the sense it takes two elements and spits out another element, that their multiplication. And this has to be associative. So the usual associative rule. It has to have a neutral element, which means an element that if you multiply with it, nothing happens. And then every element should have an inverse. And I think most people have encountered groups, probably without knowing it. The group of integers with addition. Addition is associative. 0 is a neutral element. And if n is an element, minus n is the inverse. Or like the rationals with multiplication. Now the neutral element is 1. And you remove 0 because you want every element to have an inverse, and 0 does not. Right? But okay, so these are kind of basic examples, but really group theory kind of comes to light and becomes very useful when it's talking about symmetry. So symmetry is the key word here. Groups were like defined to encode symmetry and describe symmetry. And every group is describing a certain symmetry, and every reasonable notion of symmetry can be described by a group. So here is a more picture way of seeing a group in action. So you take an equilateral triangle, and you think of all the ways in which you can move this triangle around so that the overall shape doesn't change. I have colored the 3 vertices just to keep track of what's happening, but you should think that the 3 vertices are the same. And then what are the things that I can do to modify this picture, like to move this picture around so that it looks the same? I mean, there is the do nothing symmetry. I can just do nothing to it. That's the neutral element. And then I have 2 rotations, right? This is the rotation by 2 pi over 3. This is the rotation by 4 pi over 3. And then I have these reflection along this axis, right? And these are the 6 symmetries of the equilateral triangle. What is the binary operation here is just do one symmetry after the other. If you do a symmetry and then you do another symmetry, the overall effect is like if you did just a single symmetry. And the inverse is just, if you do a symmetry, then just do it in reverse. Okay. And a very important group here is the group of, for this specific story, is the group of permutations on a finite set, which is called the symmetric group. So you have like a set of n elements for some finite number n, and this set has no structure. The only the notion of symmetry here is just like the weakest one, which is just shuffle these elements around. Yeah. And then again, identities do nothing, and the operation is do a permutation after the other. Here I have written like a simple example. So I can write a permutation this way. So these are my 5 elements, and these are the images of my 5 elements. So 1 goes to 2, 2 goes to 3, etc. And then here is another one, and then their product is just I do one and then I do the other. So for example, here 1 goes to 2 and 2 goes to 4, and in their product 1 goes to 4. Right? The inverses are to do everything in reverse. Another construction that plays a role in this thing is the direct product. So this is just a whole host of things you can do to build new groups from old. If you have 2 groups, then you can take their direct product, which is their elements are just pairs of elements in the 2 groups, and the product is just done coordinate-wise. And this is similar to how, from a vector space, you can build a new vector space just by taking products and just do everything coordinate-wise. Right. So the main focus, or a main focus in the 20th century, has been on finite groups. So groups with a finite number of elements, right? And this has culminated in the classification of finite simple groups, which are kind of the basic building blocks of finite groups. This has a huge effort that, there's many YouTube videos about this story. It's kind of taken many years, many pages of maths, and many authors. So big community effort. Now this is done, and there's still people
and that probably just talking about finite simple groups and the classification, that's probably the topic of a whole other conversation some other time.
Exactly. But the point is that, so even if there's still lots of open problems around finite groups and there's still people studying them, the main attention has now shifted to infinite groups, right? And so, we've seen examples of infinite groups here, right? Z with addition or Q with multiplication. Maybe a more complicated example is just the groups of matrices, which I think anyone has done linear algebra can appreciate. And in general, like infinite groups are much wilder. There's many less general things you can say about all infinite groups, right? There is a certain philosophy that like any, due to Gromov, that like any general statement you make about all groups is either trivial or false. It's just like a very, very wild landscape in general. So a common strategy to understand certain infinite groups is to approximate them by finite ones. Okay, we understand finite groups well. So if we have a way to take an infinite group and approximate it by finite groups, then we can borrow our understanding of finite groups and transfer it to this infinite group. Okay. And so for now, for this section, I'm just going to keep vague about what this means. But the point is that this is what the OpenAI result is about. So soficity, the property of being sofic, is a certain sense in which a group is approximable by finite groups. And we now have an example of a group that is not approximable by finite groups in this sense. So it's like very infinite in a sense, and there's nothing there's no reduction you can do to finite groups to understand it better.
I'm curious, what does it mean here to approximate?
So that's coming. So I'm going to actually like tell you the full definition. This is doable. Awesome. So before that, just like for as a high level, there's many properties of groups that you could come up with, and so why is soficity important? Why did it rise to prominence? The point is that there's tons of open questions about groups, and sofic groups are groups where, on the one hand, it's a strong property in the sense that there's many things that we don't know that we can prove for sofic groups using this kind of reduction to finite groups. And on the other hand, it's a very big class. I mean, so big that we didn't know an example until 2 days ago, right? And so there's, but the point is that, yeah, all of these conjectures still remain open. I mean, there's tons of conjectures that were known for sofic groups. Now we have a non-sofic group, but we don't know if this group actually is a counterexample to these conjectures as well. So this is like kind of not the end of the story, it's kind of the start of a new chapter in a sense. And yeah, so the solution relies, on many things, many developments in the past
by the way,
years.
Francesco,
yes,
a lot of the conversation about AI and solving things like this, some people very reductively say that math is solved, and this is what you just said is one example of you prove one thing, and now there is another like 10 new things that we don't know, that are now open again, and that there is more work for you, much more work for you to be done after even knowing an example of a non-sofic group, right?
Yeah, definitely. Right, and so the thing that I was saying before is that like there's many works that this relies on, but like the most crucial ones are work by Kuhn from 2016 and Thom from 2019. I made a point of like highlighting in green every time that there's like a person whose work is important to this, so that it's clear that this, there was a community effort. And what the OpenAI model does in very broad terms is that it takes these two papers, right, which had certain results and certain ideas, and it pushes them further. It's a kind of a clever, very technical improvement on these results. And then it gets to a point where you actually can apply these to specific examples that then can be tested. It's not out of the blue, right? So this is something that kind of was already in the air, just no one had managed to actually make it work. And another thing that I want to clarify is that the OpenAI paper is called On the Soficity Conjecture. And as far as I know, no one has ever conjectured that all groups are sofic. From the very beginning of the topic, Weiss defined soficity in 2000. And from there, already in that paper, he says probably not all groups are sofic. Okay, so it was a problem about soficity of groups and not a conjecture that all groups are sofic that has been disproved. And in this sense, it's also like slightly different from the unit distance conjecture in the sense that, this is an expected result. It's not like it's not that everyone was trying to prove that all groups are sofic and now there's a counterexample. People were actually trying to find a non-sofic group.
All right, so that's really interesting. I was going to ask you, so the Kuhn and Thom papers, are those very well known in the area?
Yeah, so I personally knew of Kuhn's paper. I did not know of Thom's paper, but I mean there are people that are more into the topic than me that were very aware about it. But like for example, they're both, as far as I can tell, only on arXiv. They have never been published. So I think they're not as known as they should have been, probably. But I mean, Kuhn and Thom themselves had been, trying to push these ideas further to a point where this could be applicable. And yeah, I mean, the point is that there's kind of so many ways in which you can take a result and strengthen it that, it's hard to know in advance in which direction you should go. And then, with the benefit of hindsight, this is something that could have been done, but, Okay, so this is exactly answering the question you asked me. Okay. And so I'm going to do it in 3 steps. Okay. There's like each one is kind of a weaker and weaker notion of being approximable by a finite group. Okay. And the kind of weakest notion is what is called residual finiteness. This is a completely classical property and extremely well studied. So you say that a group is residually finite if for every finite subset of your group, every finite chunk of your group, you can map to a finite group. Okay, and by map, that's saying that respects the binary operation. This is what is called a homomorphism in group theory. So, the map of a product is the product of the images. And this map is injective on F, so it sees all of F. Okay, so you take your big group, you map it onto a finite group, and inside this finite group, you recover all the information about the finites that you started with. Okay, this is in a sense the most natural notion of approximating by a finite group, right?
Yeah.
And maybe, I guess I didn't put it here, but maybe the most clear example is like Z itself. Z, the group of integers, you can map it to the finite group of integers modulo something, right? So if you have a finite set, let's say it's the set of numbers up to 100, then you can map it to integers modulo 101, and that map will be injected. Yeah.
Right.
Okay, so you can see finite parts of G inside finite shadows of G. This definition itself is a bit restrictive in many settings. There's a very natural weakening, which is, I mean, here we're looking at maps from the whole finite group to this, so the whole big group to this finite group. But we're only, we only really care about understanding what's happening in F. So we might not need to just define a map on every element. We maybe just only care about what's happening on this finite set F. And this leads to the definition of what is called locally embeddable into finite groups, LEF for short, which is the exact same definition, except that the map is now not from G, from the whole group G, but only defined on this small set F. The small set F itself is not necessarily a group, but what I'm saying is just that, it's something where you can multiply, and maybe multiplying you go out of F. There's weird things that could happen. But the point is that all of the information that you want on the finite set, you can still see this chunk inside a finite group. Okay, it's a small difference, but it buys you a lot more groups, and in many situations, this is all you need to kind of approximate by finite groups. Okay. So yeah, the formal definition of this is by Gordon and Bershik in 1997, but this notion was already kind of present in work of Maltsev from 1940. And
Francesco, in the definition of locally embeddable, the finite groups, is there a notion of restricting what families of finite groups appear?
Yes, and this is exactly what we're going to do now. Yeah. Right. So I mean, to a sense, yes, you can restrict families of finite groups, and that gives you more restrictive properties, right? Where you can say more. But now there's a natural restriction that you can do to a certain class of finite groups that we have seen that actually does not make the notion more restrictive, and that is sorry. Maybe before I go on, an important thing about this definition of LEF is that there are many examples of non-LEF groups. Okay, not only are there many, but they're easy to come by, and this actually plays a role in the solution. Okay, so I'm not gonna give one. That would be complicated, but like anyone that kind of has done some infinite group theory, knows about groups that are not LEF. So this is an approximation property where it's easy to find non-example. Okay. So for the next generalization, we need the following fact. So this is a classic theorem of Cayley, which says that every finite group embeds in a symmetric group. So embeds just means that there's a map that preserves the binary operation, so a homomorphism that is injected. Okay. So what we're saying, one way to say this is that this Q, this finite group Q, can be realized as a subgroup of the symmetric group Sn. Okay, it's like a substructure. It's sitting inside, respecting the group multiplication. Okay, so because of this, if in the definition of residually finite and LEF we change the group Q by a symmetric group, we get the same definition, because you can just take the approximation that you had here in the definition and then just compose that with the embedding of Q into the symmetric group, right? And so it's not restricting the generality. So yeah, in both these definitions, you can just take Q to be a symmetric group, Sn for some number n. Okay. And now this leads to a natural generalization of this, because instead of talking about maps that respect the binary operation on the nose, we can talk about maps that almost respect the binary operation, okay? And this is something that we can make sense of inside the symmetric group. So instead of saying that, the image of a product is the product of the images, instead of this equality sign, you're just going to say that these elements are close, okay? And to quantify what it means to be close, we need a notion of closeness in this symmetric group. And that is what's called the normalized Hamming distance, which is this. So the distance between two permutations of sigma and tau is the proportion of elements on which they disagree. Okay, so this is a very natural notion of distance that appears all over the place in computer science, probability, etc. Okay?
Yeah, that makes sense.
So if I have, for example, if I have two, you can see that if sigma and tau are the same, then they will agree everywhere, and so their distance will be 0. And then the permutations that are the furthest apart, they have distance 1. They're the ones that like don't agree anywhere. Okay. Okay, so now we can define what a sofic group is. So again, we're talking about approximating a finite subset of the group. But now we also introduce a parameter of like precision with this epsilon. Okay. And now that we want a map from the finite group to Sn, such that instead of saying that it respects the binary operation, we say only that it almost respects the binary operation, in the sense that the distance between the image of the product and the product of the images is small, smaller than epsilon, this epsilon that we have specified at the start. And then before we asked that the map should be injective, now we ask that it is very injective. Okay, there's many ways to formalize this. Let's just say that, you know, everything, like the distance from the identity is bigger than a half, which means, sorry, maybe I should specify here. For G in G different from the identity, which means that like the image of every non-identity element should move at least half of the points. So this sounds like you're asking for too much, because before you were asking just for injectivity and now you're asking for Stronging injectivity. But the point is that if you don't ask for this, then you could just, you know, very easily verify this by just taking a bunch of permutations that move a very, very small percentage of points. Yeah. And then this first thing about almost respecting the binary operation would be automatically satisfied. Okay, so this is kind of if you want to switch to an approximate situation where you only ask for approximate multiplicativity, then you need to strengthen the injectivity requirement for this to be a reasonable notion. Okay, so that's the notion of soficity. Okay. Okay, so yeah, this was introduced by Gromov and Weiss in 1999 and 2000. Gromov was using a different term. Weiss kind of formalized it more clearly and introduced the word sofic. The word sofic comes from the Hebrew word for finite. So, Weiss is Israeli. And what we have seen so far is that we have this property, residual finiteness is stronger than LEF, and LEF is stronger than sofic. Okay. There is the reason why there's so many examples of sofic group is that there's another property that I will not talk about, but it's called amenability, and it's very closely related to the Banach-Tarski paradox. And this property also implies soficity. So and it's unrelated to residual finiteness and LEF in a sense. So you have kind of these two big classes of groups, and both of them fall under the umbrella of sofic groups. And moreover, there's many ways of taking sofic groups and building new sofic groups out of them. For example, the construction that we saw before of the direct product that preserves soficity. And yeah, okay, so the point is that now we know that not all groups are sofic. Okay, and then just to add a bit more detail to what I said before, yeah, there's many conjectures that are known for sofic groups, and that's why soficity got so much attention. In fact, that was the motivation to even define soficity at the beginning. There's this conjecture about cellular automata that is called Gottschalk's surjectivity conjecture that is still open. And this conjecture was known for LEF groups and for amenable groups. And soficity was introduced as a kind of common generalization for both that still satisfied the conjecture. And there's many other conjectures that are known for sofic groups, and they're still all open. And moreover, there are further weakenings. So this is just like one notion of approximating groups by finite groups. There's weaker notions, and whether any of these...
One thing about your previous remark. So
yes.
This new example, you said we don't know that it's a counterexample to these conjectures, right?
No, we have no idea. Yeah. In fact, the proof method kind of doesn't tell you anything about these conjectures. If you wanted to attack any of these conjectures, or if you wanted to prove that there's a group that is not just non-sofic, but it does not even satisfy one of these weakenings of soficity, then what you would have to do is not understand the OpenAI proof better, but understand the work of Kuhn and Kuhn-Thom better. Okay, so like their work was about sofic groups, and that's the work, this human part of the proof is the part that we're missing to attack these conjectures in a sense.
I see.
Okay, and yeah, so that's all I have for the definition, and then now I can, if you want, I can tell you very vaguely how the proof goes. So here is the general approach in general, like that, it's a kind of reasonable way to go about this, is that there's two steps. So first, you want to prove a theorem of the type: if group G is sofic, then group H is LEF. What you're doing is that you're taking this very weak notion of approximability by finite group, which is soficity, and you're saying if this group satisfies this very weak notion, then this other group satisfies this much stronger notion of approximability. It's kind of you're kind of improving it. And then you find a situation where you have where this theorem applies, and you already know that H is not LEF, because as I mentioned before, we know very well how to construct non-LEF groups. Okay, we have a large source of these. So these are the two things you need to do. Yeah, and these are not two things that you can do separately, in the sense that there's many situations, there's many possible statements of the form 1, and many of them might be false, and many of them might be true, but like have no concrete applications where concrete settings where you know how to apply it. So you kind of need to find the right statement of the form 1 that is like, strong enough that strong enough and flexible enough that you can both prove it and find the examples to which it applies. But there are statements of this type that have appeared in the literature for a long time. So the general idea of kind of this improvement of as an approximate thing to a more exact thing is related to what is called like stability in group theory, which is something that even von Neumann and Turing and Ulam already were studying, right? So this is something that goes back a long time. And in this form, like as an approach to find a non-sofic group, it appears in work of Glebsky and Rivera from 2009 and Argencer and Paunescu from 2015. Does this idea of kind of improving soficity to residual finiteness or LEF-ness would be a good way to find a non-sofic group. And in fact, this has seen success in the past, this approach. There are other notions of approximability that are kind of unrelated to soficity, but like in the same spirit of being able to approximate groups by other things. And in these settings, these kinds of results of improving an approximability to a LEF or residual finiteness have led to constructions of non-approximable groups. So here are 3 results in the past few years that use this philosophy to do this, but this philosophy so far had not worked for sofic groups. So there are 2 theorems of this type that are important here, the ones that I mentioned before by Kuhn and Kuhn-Thom. So first, just the statements are going to be technical, but I'm just gonna give you an idea of what they mean. So 2 technical terms that appear. So a sofic approximation is a proof of soficity. So the definition of sofic is about the existence of certain maps, right? Mm-hmm. So and that's what a sofic approximation is. And another group property that I think it's maybe too hard to get into, but it really plays a key role is this property that is called property T. It's one of the most important properties in modern group theory, which was defined by Kashdan in 1967. And this plays a crucial role in the proof, but I will not get into what it means. Okay. So here's the theorem of Kuhn. So it says that if you take a property T group, so a group with this property, whatever it is, and you suppose that it's sofic, right? Then it has a sofic approximation of, there's a proof of soficity, and it's saying that this sofic approximation has a very special form. So this very special form is saying it's close to a disjoint union of expander graphs. again, so I'm not going to get into detail about this, but just think of it as if a property T group is sofic, then it's sofic in a very special way. Okay, and this very special way
is in terms of the Hamming distance.
Yes. You can kind of change the sofic approximation a little bit to make it into a disjoint union of expander graphs. I mean, there's a way to associate graphs to sofic approximations, and then expander graphs are like very nice graphs. Right. So yeah, the point is, if a group with this property T is sofic, then it's sofic in a very special way. Okay. So there's the result from 2016 that in the AI paper is cited as a result from 2019. I guess that something went wrong in the prompt there, but then
just for reference, like where did Kuhn paper? Where did it appear? What journal? You know?
It's so both of these key ingredients are only on the archive, as far as I can tell.
Oh, okay. So they're not...
I actually don't know why they have not been published. I mean, these are two very clearly publishable papers that very respected in the community. I'm not sure if they're what the story there is. I wouldn't want to speculate.
Right.
Okay. Okay, and then here is the result of Thom. So again, this property T appears. Maybe let me highlight again these terms. So property T and expander graphs. Okay, so now suppose that K is a property T group and J is some other group. And you look at the direct product. So remember this notion of like building a new product, new group out of old ones. So suppose now that it has a sofic approximation. So there's a proof of soficity for this. A proof of soficity of a group gives you also a proof of soficity for any subgroup of it. Okay. So given a sofic approximation of this product, there's also an associated sofic approximation of this group K. And now suppose that this sofic approximation is an expander graph. So whatever this notion of expander graph is, the key thing is that up here we have a disjoint union of expander graphs, and here instead we have a single expander graph. And the conclusion is that under this hypothesis, J is linear. Okay, so this is exactly the kind of statement that we wanted from before. And as I pointed, the discrepancy here is that Kuhn gives you a disjoint union of expander graphs, and then Thom gives you the conclusion that you want, but assuming that there's a single component. It's not a disjoint union, it's just a single expander graph. Okay. And the main step of the solution is to bridge this gap, to go to kind of get into a situation where you actually have, from many components, only one component under certain additional hypotheses. So this is the key step in the paper. It's proposition 2.3. So I have now two property T groups, okay, and then some other group, and the product of the first group gamma and this group J is embeds into G. So it's a subgroup, it's sitting inside. And then there's a bunch of technical assumptions. So gamma should sit very nicely inside G, and there's some kind of self-similarity that is happening between these groups, some groups that kind of sit inside themselves and stuff like that. And the conclusion is that if all of these nice assumptions are satisfied and G is sofic, then you can conclude that J is linear. And this is really what it's doing, is that it's taking as a starting point the theorem of Kuhn to get these disjoint unions of expanders, and then kind of modifying it and massaging it a bit to get to a point where you can identify a single big component, and then this single big component is going to be an expander where you can apply the Kuhn-Thom theorem. And this is the key step. This is the most technical step. And if there's one thing that I want people to remember, is that this would not exist without the work of Kuhn and Kuhn-Thom, right? So this is really like taking their work as a starting point and their ideas in the proof. Yeah? It's a great result. It's a great achievement. It's a very clever and technical proof, but it's definitely a big misrepresentation to say that there was no progress in a decade. These two big progresses are used essentially in the proof. Yeah?
The ideas of the proof itself, do they just resemble also methods that have been used in Thom, and in other works in
yes,
this area?
Yes. I mean, yes. It's just like a clever combination of known techniques. I mean, the main point is that, like, the hard thing more than the proof is to come up with the right statement, right? This proposition is one that, like, if like an oracle came down and gave it to Kuhn or Thom, they would probably be able to prove it in one day. Yeah. I mean, maybe not me, but they, I'm sure they would have, right? But the difficult here is to come up with the right statement, right? There's just so many ways in which you could, this is very vague, but if you go look at the paper, like, there's a bunch of technical assumptions, and there's an infinite number of statements that you could make this way, right? And to come up with the right one that you actually want to sit down and spend time proving, and then that actually is applicable in a concrete setting, that's the part that people have not been able to do, and the part that on which AI has an advantage over us, because AI gets to try a billion things and just see what works, right? While we don't get to try a billion things, we kind of have to do things step by step. And after this, the point is to find a situation where this configuration here occurs, and you know that J is not LEF, and then the proposition tells you that G is not sofic. And the specific example OpenAI comes up with is using some things called leave-it algebras and Thompson groups. And this is very elegant, and to me was very unexpected when I saw this. I work a lot on Thompson groups, and I didn't know of this connection with leave-it algebras. It's very nice. It's very cool, but it's not necessary. So now that the paper has come out, on my homepage you can find a much simpler version, I think, of this last step, which puts, for me, the focus, like, I think that the focus should not be on these leave-it algebras and Thompson groups. That sounds very cool and fancy, and is very elegant. It's a very elegant way of solving it, but there are, more simple-minded ways of doing it. The key is really this proposition. This is the big novelty. This is coming up with, and as I said, it's really, finding the right statement that is the thing that mathematicians have not been able to do.
In the connection between leave-it algebras and Thompson groups that you said is unexpected and elegant, is that?
I should say that it wasn't expected to me, but it does appear in the literature. Yeah, it's something that has been
there.
The connection between leave-it algebra and Thompson groups. Yeah, I didn't know about it, and I think not many people knew about it, but I have found at least 3 papers that exploit this connection to prove counterexamples to other things.
So, like, in other examples of these AI generated proofs, it's making a lot of, like, interesting connections between pieces of literature. It's able to look through all the literature at the same time and make all the connections, basically, that it would take us some random walk to find ourselves.
Exactly. Yes. Yeah. Yeah, and also maybe one thing is that this is just speculation, but, like, one might ask, why did it come up with leave-it algebras and Thompson groups as an example instead of, like, this more simple approach that I was saying? And I think the point is that, the more simple approach that I was saying has to be, there's a caveat that it's much simpler once you know the right things, which people in my field know very well. Many of these things are probably not fully formalized in the MathLib in Lean. And, here everything was done by, the statements that can be more easily formalized are there's a bias towards them in the MathLib, right. For OpenAI. And this is kind of an unexpected connection that, like, once you make the connection, then it's quite elementary in the sense you don't need big, you don't need to assume anything big to prove it. And so this is probably why it came up with this. It's kind of doing this conceptual jump to get to a point where it's easy to formalize.
That's an interesting restriction that I had not thought about. That somehow they're also looking for proofs that they can auto formalize quickly, right? So they can actually also publish a certificate that the proof has been formalized.
Exactly. Yes. I mean, this is my speculation because, like, I think with other people that I've talked to, like this approach that this other approach is like more natural in a sense. It's like if many of the people I know, if they were presented with the statement of proposition 2.3 and they were asked to find a way to apply it, they would probably come up with something more similar to this than with this connection to Libet algebras and Thomson groups, right? I know few people that would like naturally come up with that. So this is just my conjecture of how of why this worked this way.
Was the result from OpenAI shared with some experts ahead of time?
Yes.
Ahead of the release?
So the timeline is, I think, on maybe Friday morning. They sent it to a bunch of experts. In particular, they sent it to some people that have proved out very closely related results. That is called the Aldous-Lyons conjecture. And my understanding is that some of the people involved in this project had heard about this conjecture from learning about this other result, and that's why they shared it with them. But I got it from a bunch of different sources, not directly from them. So I think that within a few hours it started making the rounds a lot. Like it was, it's a very sensational thing. So it's people were very impressed and everyone wanted to get to look at it. But I mean, there are some specific people at OpenAI. I guess I should probably not name them. I don't know, because since their name does not appear anywhere on the website, I imagine that they want to. I mean, I have some issue there. I think there's some issues of transparency there. That there's like no person that you can contact about this. Unlike in every math paper, everyone is free to contact the authors. They always put their emails on the papers, but here only if you're in the know, you know who to contact. But anyways, they contacted these people for comments. And one thing I can say is that like no group theorist was involved here, as far as I can tell. And in fact, the first version of the paper that was sent around, I sent some comments, and there were some things in this paper that made it clear that this was not written by people that knew about this topic. So there were some kind of, many citations missing, of things that definitely should have been cited. And there was like a certain insistence of like a small improvement to this theorem that is like immediate for people that know, but it was like iterated like 5 times throughout the paper, which again, I think it makes it clear that it was not people that knew about like what the really important things in the problem are. And and then I and other people sent back some comments. And this was all on Friday. We were told that the paper would come out on Monday. I was kind of trying to, with some colleagues, to put together a community response, kind of like the one for the unit distance problem. The idea was to do it this weekend, but then the result came out on Saturday morning already.
Is that still coming? Some community response?
I don't know yet. I mean, there's a big email thread with lots of thoughts, we'll see if we manage to organize them into something coherent and useful. I mean, I think many people in the community have many thoughts. We'll see about how this happened. I mean, the issue is a bit that this OpenAI imposes a sort of very tight timeline where I'm not used to working this way. I think nobody is, of like receiving something and then having to respond immediately, and everything done within 24 hours. And this is the kind of thing that would benefit from a community response that is crafted over the course of a month or something. But maybe in a month, like there's gonna be another set of problems that is solved, and then the attention is completely shifted away from this one, and then what's the point of doing a community response? So yeah, this is all very fresh, and I don't know what's going to happen. I thought that this kind of note that I put on my homepage was like a kind of a tiny response that was helpful immediately to kind of shift the attention away from this, fancy looking and mysterious looking connection between Libet algebras and Thomson groups, and put the focus on this proposition that is the one that is really benefiting from the work of Kuhn and Kuhn-Thom.
And that paper of yours you've put together since like Friday morning?
Yeah, I mean, I got it on Friday morning, and I posted it, I guess, yesterday on my homepage. Yeah. Yeah, I mean, full disclosure, I didn't sleep on on Friday night, and yeah, just try to understand this better, and really try to understand the role that the different parts of the proof had, and yeah, this is what I came up with.
Can you tell me about the consensus about, in the people you know, or your own opinion of what the importance of this result is?
Yeah, so I mean, the result is definitely, it's definitely a breakthrough. It's definitely very important. This is like something that I think anyone would accept in the annals. I mean, this goes without saying. Like it's definitely a very important thing, something that many people have tried to solve for a long time, and yeah, the I think more than the like to me and I think to other people personally, I mean, I think more than this specific result, I think what we should do is like celebrate and try to understand better the work of Kuhn and Kuhn-Thom, because that's the stuff that would need to be understood better in order to push the field forward. There's tons of conjectures that are still open, and tons of things that we still want to find, and yeah, the human part of the proof is the one that needs to be really understood and developed in order to push progress forward. And so yeah, one other thing is that I mean, this is maybe not the right analogy, because I know that would have like much bigger implications, but like you should think of this as someone has found a zero outside of the critical line in the Riemann zeta function. It's very different from proving the Riemann hypothesis, right?
Okay. In the sense that's a big comparison right there.
Yeah, so I mean, I think it's not the right comparison, because I think finding a zero outside would actually have like consequences. This is like even less so. Like this example specifically on its own does not have many big consequences. It's just like answering. It received a lot of attention, and it is very so impressive because it's something that we have tried as a community to work on for a very long time and have not managed to solve.
But as you said before, there was no conjecture that said all groups are sofic.
No, yeah, on the contrary, yes.
There would be a counterexample, but nobody was able to find it.
Yes, correct. I mean, if you go on the paper of Weiss from 2000, the one where the word sofic appears for the first time, I mean, he explicitly says most like something like it's probable that not all groups are sofic, but I haven't been able to come up with an counterexample. And I think if you look at the way that the literature has been going for a long time, it's very clear that everyone was expecting this. Sometimes this is explicitly stated. Sometimes this is implicit in the fact that people were trying to come up with statements of the type, if this group is sofic, this group is Aliyev, right? So that's the kind of thing that you really makes sense to investigate if you're looking for a counterexample. There's many important groups and natural groups that were believed to be good candidates for a counterexample. It's still very interesting to determine if those are candidates for a counterexample. This doesn't say anything about them. It's always useful to know that groups are sofic, because then it has all of these implications. This doesn't tell you that any more groups are sofic. And this doesn't tell you anything about all of these generalizations of soficity.
Well, thank you very much for helping me understand what's happening and to digest the proof a little bit. That's Terry Tao has been saying for a while now, this sort of digesting of the proofs is the most important part now, or we should move to value these kind of digestion. And I was actually wondering if in the write-up from OpenAI, do you think they do some effort to try to explain this proof, or does it take people like you to understand what's actually in the proof?
So I should say that there was a very very approximate effort of this form in the introduction of the first version I saw, and then we also sent collectively some comments. I don't know if anyone has like sat down and absorbed these comments, or they have just been fed into into the model. Most likely the second one. But in the new version, the introduction is much longer, and it cites a bunch of related literature and related results, and it gives an overview of the proof that is actually telling you something is kind of useful, which the previous version did not really. But as I said, I think it takes the community to actually recognize what the important steps are. And for example, in that introduction, I think that the emphasis on Leavitt algebras and Thompson groups kind of is not the right place to put emphasis on. The right place to put emphasis on is the generalization of Kuhn and Kuhn-Thom, but of course, that looks less fancy because it's a generalization of something that was already in the literature, and not like kind of this big new idea.
Right. That's another important point where OpenAI wants to what they want to emphasize. Of course, they want to emphasize the work of the model. Anyway, thank you very much, Francesco, and I hope
thank you.
I get to talk to you some other time about AI in general.
Yeah, with pleasure.